In this video, we're going to look at floating point arithmetic. We're going to look at how we write floating point literals for both decimals and doubles, how to do basic arithmetic on floating point value, and more detail of why do we have two different things? Why do we have both doubles and decimals? Right? The most important thing to know about the difference between doubles and decimals, which are the two primary floating point types you use in C#, are use doubles for calculations that involve physical quantities like length or speed or mass or electrical current or whatever, some physical quantity, and use decimals for financial calculations always. Right? You don't ever want to be representing a price as a double if you can possibly avoid it. Right? And I'll talk about why that is later on in this video. But let's just go into Visual Studio here, and I've shown a bunch of different kinds of literals here. Right? So you can see we've got a decimal variable called dollars, and it is $123.45, and it ends in M. Decimal literals always end in M. The mnemonic to remember that is M is for money. Okay. Now it's legal to end doubles in D for double. Though it's very rare to do so, right? So we have here, width and length, 345.0. Right? It's very common if you have a round quantity that you would like to be a decimal to add a 0.0 to it, because that's a hint both to the compiler and to the reader of the code. No, really, this is a decimal. I did not intend this. This is a double, rather. This is a floating point quantity. I did not intend this to be an integer. Right? Most common is to see just the 0.0 or whatever value it is without the D. The D is optional. Now there's also a syntax for doubles. You can see here we've got this double in scientific notation. Right? So this is 1.346346 times 10 to the 15th power. Right? So the E here means exponent, and the thing that follows the exponent is an integer, right? And it can be positive or negative. If you wanted a very small quantity, that could be to the negative 15. Right? So you can see why these are useful in scientific notation, because when you're doing physics problems, you often end up having to multiply by very large or very, very small things. Right? Now, if you want to use the operators, that we discussed in the previous video, the less than, greater than, less than or equal, greater than or equal, equality, inequality, plus, minus, times, divide, all of those operators work on floating point values the same way as they do with integers. There is a remainder operator for floating point values. It is almost never used, because the reason why you would use the remainder operator is precisely because you're doing integer division and you would like to know what the remainder was. Right? So even though the remainder operator does work on doubles, I've personally never seen anybody use it. Now you can mix integers with doubles or decimals just fine. Right? So here we have an example where I've said we've got a double. It's the area of a triangle, and I've said the area of the triangle is the width times the length divided by 2. And C# will figure out here, it's like, oh, it looks like you have this quantity, which is a double, and this quantity, which is a double. Their product is a double. You are dividing by an integer, but I know how to make that integer into a double, and so it does so automatically. Right? So you don't have to put the 0.0 there, although it is perfectly legal to do so if you want to. Right. Now, something that's not legal is it is not legal to mix doubles with decimals. Right? So if I uncomment this code here, I have a decimal. Right? It's the price per meter. Right? And I'm going to say the price per meter is dollars, right, which is a decimal. And I'm going to divide that by length, which is a double. And C# gives me a red squiggly in the IDE, and it says the division operator cannot be applied to operands of type decimal and double. Right? And the reason for that is because decimal values are almost always financial values and double values are almost always physical quantities, it usually does not make sense to add, subtract, multiply, or divide them, although this division is the one that makes the most sense. Right? So also, it's not clear from this what should the type of dollars divided by length be, right? Clearly, whoever wrote the code intends it to be decimal, right? But like I said in the very early video, part of the design process of C# was to figure out what mistakes are people likely to make, and then make those things illegal, right? Make the compiler call out, you are doing something dangerous and weird here, right? So since it's not clear whether the type of this thing would be decimal coming out the other end or double coming out the other end, it's simply made illegal, right? Now, suppose you really do want to do this, right? You want to say, no, really, I want to divide dollars by length, I want to get a price per meter, and I want the result to be a decimal. Well, C# has a special operator called a typecast that lets you do that, right? So here we can say decimal price per meter is equal to dollars divided by, and then we put before the length expression, we put in parentheses the name of the type that we wish this thing to be, right? So this is saying this thing is really a double, right? If we hover over it, we see that it's a double. We would like it to be treated as though it were a decimal, so we're going to say, really, C# compiler, treat this thing as a decimal. I mean it. This is not a mistake, right? And now what we have is now we have dollars, which is a decimal, divided by length, which is a decimal, and the result is a decimal. So this kind of expression is called a type conversion expression, or a cast expression. Now, there are some conversions. We saw earlier that you could convert an integer literal to double. You can also convert an integer literal to decimal implicitly, right? The compiler figures out this is always safe. It is perfectly legal for this to happen. There are some conversions which are dangerous, like the double to decimal conversion. They're either dangerous because they can potentially lose information, or because it just seems semantically wrong. And in those cases, those are called explicit conversions, and they require a typecast operation. A lot of people in the programming language community use the word cast to mean either kind of conversion. I personally try to reserve using the word cast to only apply to situations where there's a cast operator in the code, where you have this syntax where you have a type in parentheses that precedes an expression. Here I have a double that is equal to 1/10. It's 0.1, right? So you might wonder, well, what happens if I add 1/10 to 1/10 to 1/10 to 1/10 10 times, right? I'm going to put that into a variable called 1. And then I'm going to ask myself, well, is this equal to 1? Is 1.0 equal to my variable 1? Well, let's put a breakpoint after the call to console.write line, and we'll run this thing, and we'll see what happens. It says false. That's maybe a little bit unexpected. What the heck is going on here? Well, the reason decimal is called decimal is because decimal is completely accurate when the quantity is a fraction where the bottom of the fraction is a power of 10. A double, it turns out, the way it's implemented in the floating point chip, which is on the inside of everybody's computer now, it represents the floating point number as a fraction where the bottom of the fraction is a power of 2. Now, 0.1, 1/10, cannot be represented as a fraction that has a power of 2 on the bottom, because 1/10 has a 5 on the bottom, right? That's 1 divided by 5 times 2. There's no way to multiply together 2's to get 5. So what happens is the compiler picks the fraction that is as close as it possibly can get, given the amount of memory that's available for a double, to 1/10, right? So it introduces a very small error, an error that is absolutely minusculely tiny. It is about 1 part in 10 to the 15 for this number 1/10 here, right? So if you're thinking about physical quantities, right, there is no scientific experiment you could do that would be accurate to 1 part in 10 to the 15. Most scientific experiments that you do, most measurements that you take are accurate to 1 part in 100 or 1,000 or 1,000,000, but they're certainly not accurate to 1 part in 10 to the 15. Right? So this tiny little error is totally unimportant for any physical calculation. But if you can imagine that we were doing a financial calculation here, it would be very strange to add 10 dimes together and get something that was not exactly 1. Right? If we did this same computation in decimals, we would find out, and let's actually try it. We would find out that we do get exactly 1. So we can say that this is a decimal, change that to a decimal literal, change this to a decimal. All right, and now if we run this program again, change that one to a decimal. And now if we run this program again, then we can see this time it's true. All right, now the same thing is true for decimals, right? I said before that decimals are quantities that are fractions, where the bottom of the fraction is a power of 10. So if we say, well, I'm going to make a decimal 1/3, and it's equal to the decimal 1.0 divided by the decimal 3.0, we have exactly the same problem, right? This thing is going to be rounded off to the value that is as close as possible to 1/3. And then when we add these things together, we're not going to get 1, right? So if we actually run this code, we can see what this prints out. So you can see it prints out 0.9999999999999. Quite a lot of 9s there. Where doubles are accurate to roughly 14 or 15 decimal places, decimals are actually accurate to 28 or 29. There's a lot of precision available in a decimal. In fact, I have prepared this handy chart for you here that shows exactly what the differences are between decimals and doubles. Right? So the largest possible decimal is roughly 10 to the 28. The largest possible double is roughly 10 to the 308. So enormously larger range. Right? The smallest decimal that is larger than 0 is exactly 10 to the negative 28, which we would expect, because that is a fraction that has a power of 10 on the bottom. In fact, it has 10 to the 28 on the bottom. The smallest double that is not 0 is 10 to the negative 323. So again, an enormously large range for doubles, right? Just the size of these things is really geared towards physics calculations where you could expect to have quantities that have these enormous exponents in them. For decimals, it seems, since they're mostly used for financial calculations, it seems unlikely that you are ever going to do a calculation that requires more than 28 decimal digits of precision for a financial calculation. The fractional base for decimal is 10. The fractional base for double is 2. The size is different, right? So if you have lots and lots of these, right? If you have hundreds and hundreds and thousands or millions of decimals or doubles that your program is manipulating, the decimal takes up twice as much memory as the double takes up, right? So you can see the effect of that much larger precision dwarfs the effect of the much larger range, right? Having larger precision requires much more memory than much larger range does. Decimals are slower than double calculations, but that is not a good reason to choose decimal over double or double over decimal. Choose the one that makes sense for the domain that you're doing the computation in, and then see if your performance is good enough. And typically, even though decimal is slower, hundreds of millions of computations per second is still pretty fast. It's not billions, but if you need to do more than several hundred million computations per second, you are writing a pretty fancy program. And finally, we're not going to talk too much about this in this course, but double has a facility to represent quantities that are either infinite or are not a number at all. So you think about 0 divided by 0, for example, right, would in a double be represented as nan, as not a number. 1 divided by 0 would be represented as infinity. There is no such concept in decimals. So summing up, always use decimals for financial computations. Always use doubles for physical computations. Remember that doubles can round off in unexpected ways. People don't usually expect that things that round off to fractional powers of 10 are going to be rounded. But for doubles, they almost always are. Decimals are not. But of course, they are rounded off if you have a fractional power of 3, for example. Right? C# disallows accidental mixing of doubles and decimals in the same expression. If you do have to mix doubles and decimals because you're dividing length by price or something like that, then you can always use a cast operator.